Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, this is Mr. T and a tutorial today on logarithms and exponential equations. So let's get started. Logarithms are a new kind of function for us, and also a new kind of operation, and they're the inverse operation of exponentiation. What I mean by inverse, when we worked with, say, quadratic equations and we were working with an x squared, if we wanted to undo the exponent of 2, we use square roots. When we're solving simple linear equations, if we want to undo a multiply operation, we use division. So those are referred to as inverse operations. So now that we're working with exponential equations, we started talking about exponential growth and decay in the last lesson. We have equations like these, and we might want to solve or work with x. So we are going to convert forms. So this is called exponential form. And we may convert exponential form into logarithm form. And you can see by the pattern on the screen how we make that change. Sometimes we will go from logarithm form to exponential form. We'll have examples of that also. So our log function has the name of the function is log, and there's an infinite number of these log functions. So we're using subscripts. So just like in our last unit on sequences and series, we identify the various terms or the various versions of the log using a subscript. This subscript is called the base of the logarithm, just like up here, this is the base of an exponential function. So when we convert from an exponential function, whatever the base of the exponential function is, that will be the base of our logarithm. So this will go to our subscript. And when we do the inverse operations, the exponent will move over here, and the y will become the variable in the log function. So it's kind of a crisscross function. So the x's change places, and the y's change place. So kind of a crisscross. The bases stay the same. You're going to want to get good at converting from both directions to solve problems. So let's practice that. So here we have two statements that are in logarithm form, and it's asking us to rewrite it to exponential form. So if we use from the last, this is the base of the log, so it becomes the base of our exponential equation, and now these two things are going to crisscross. So the exponent will be the 2, and the term that was part of the log function will go over here. Now, if we calculated 18 squared, it's going to equal 324. But here, we don't want to do that. We're just working on converting forms. So again, here, our base will stay the same. And these two numbers will crisscross. So we've got -2 here and 1 over 324. So again, 18 to the -2nd power would equal this. Now, if we go from exponential form to log form, this is our base, so we are going to have log base 11, and the exponent and this number will change places. Now, sometimes we will, when we do logarithms, have our number that we're taking the log of in parentheses, and sometimes not. It can go either way. And over here, again, we do the same thing. This is our base. So log base 20, and we're taking the log of the fraction here. So again, we're changing sides of the equals. Kind of, I think of it as a crisscross. Now, if I go back to the last slide, I skipped over the bottom of this, But if we look at this logarithm, what it's asking is, or what it's determining, the value of this logarithm is an exponent, because this x came from up here. So it's providing the exponent that we would raise the base to, in this case b, to obtain a given value. So again, if I see log base b of y, it's asking what exponent would I put on b, the base, to give me this value. So we can use that statement or that understanding of logarithms to evaluate some logarithms without using a calculator. So again, if we use that, this is asking 3 to what power equals 81. Now, to work this, we need to understand that 81 is a power of 3. You might know it as 9 squared. But 9 is 3 squared, so we have 3 squared raised to the second power. So I'm replacing the 9 with 3 squared. And we use our exponent properties that we had in the last unit, or in the last marking period, and we multiply our exponents here. So our value, we just determined the value of this logarithm, the log base 3 of 81, is 4. So likewise over here, 4 to what power, we can give it a variable here, equals 1 over 64. So now to do this, we need to write 64 as a power of 4. So 64 is 4 to the third power. And we can use our exponent property. Now this 4 is in the numerator, so I want to move this 4 to the top. So we use another one of our exponent properties. Remember, when we change a term with an exponent to the other side of the fraction, we change the sign of the exponent. So now our exponent here on the 4 is negative 3. So again, log base 4 of this is saying that 4 to the negative third power equals this fraction. Now, most of the logarithms that we work with in everyday problems, let me fix this here. I didn't fix this type. So this is log base 10 with the subscript, and this is log base e with the subscript. So anyway, as I was saying, most of the logarithms we work out aren't going to be nice numbers like we worked in the last problem where they come out to be perfect powers. So we're going to have to use a scientific calculator to calculate logarithms. So a little bit of terminology. There are two common or normal logarithms that we use called the common log and the natural log. The common log has a base 10, and it's abbreviated as log without a subscript. So if you see log without a subscript, that's referring to log base 10. We also, in our exponential growth models, use the natural number e for continuous compound interest. So here we have log base e, and it's abbreviated as ln, or sometimes people call it the len of a number. So if I bring a calculator over, we can see here we have a log button that we can use to calculate the base 10 log of a number. And here we have the ln button, or the len button. We can find the log base e. Those are the only two log buttons on the calculator. So if we have any other logarithm, any other base 2, base 1/2, base 30, whatever, we have to use this formula to convert from one base of a log to another. So it's called the change of base formula, because we're converting our logarithm to base 10 common logs. And we do that by taking it as really this calculation. So in the numerator, the top, we have the log base 10 of this number. And on the bottom, we have to take the log base 10 of the whatever the base was. So we're going to use that in a second. So let's evaluate a couple logarithms here using our calculator. So this is a common log. So all we have to do is press our number here and enter our function value, our argument, and if we round that to the nearest 1,000th, this would be 1.839. Okay, here ln, there's a button for that, so it's very simple. And if we round that to the third decimal place, we've got here 4.205. Now, this is not a log base 10 or log base e, so we don't have a button. So we're going to have to use this change of base formula. So it's going to become the log of 12 divided by the log of 4. Now, when we use the calculator, we have to be careful. It's not the log of 12 divided by 4. It's log. Now we have to close that parentheses. Now our divide, and then again log of our base, which is 4. And that is 1.792 rounded. So again, we could check our work. Our definition of this log is 4 to what power? That would be this power equals 12. So if I raise 4 to, I'm going to use our rounded version here, 792. Now, because we rounded this logarithm, we don't get exactly 12, but it's very close to 12. Okay, let's just do one more. Move this over here. So again, we're going to rewrite this using our change of base formula into this calculation. And now we can just calculate that. So log of 4.7, don't forget to close your parentheses. Now divide, and we do our denominator. And this time we get 2.233 when I round it to 2 decimal places. Okay, one of the prime uses of logarithms is in solving exponential equations. Now, the first version of these exponential equations we're going to solve doesn't require logarithms. Our second version that we'll wrap up this tutorial with will use logarithms. So we're going to have two kinds of exponential equations. This first type I call power equals power. So we have a term with an exponent equals another term with an exponent. Now in this case, these exponents over here are just 1, but this we could have a exponent with a n in it over here. So the procedures that we're going to talk about would be the same. What we want to do is we need to rewrite each of these bases to be a power of a common base. So in this case, the easiest version, 16, is a power of 4. So we can write both sides with the base of 4. Now, if you have an equation, so these two sides are equal and they both have the same base, then that means for these to be equal, these two exponents must be equal. So we can just simply take the two exponents on the two sides, set them equal, and solve that equation. And we get here n equals, I had to divide that by negative 2/3. Now if we look here, 27 and 9, we cannot write 27 as a power of 9. We cannot write 9 as a power of 27. But these are both powers of 3. So 27 is 3 to the third power. Now we just replace the 27, so that is still to this exponent here. And on this side, we can write 9 as 3 squared. Now we need to simplify our exponents here. We want this to be 3 to an exponent. And if you remember from our last marking period when we had a power to a power, our exponent properties are we multiply these exponents. Now when I have a number times an expression, I need to distribute. So if I use this property, I'm going to multiply 3 times both, so I get 9 to the n power, 9n minus 6, and that equals 3 squared. Now we have rewritten this to be the same base. So since we have the same base and we have equals, then our exponents must also be equal. And now it's a simple linear equation that we can, so I'm going to add 6, solve for n, divide by 9, and we get n equals 8/9. Okay, so that's one type. Now our last type of equation we're going to look at here are exponential equations with a single term. So these would be equations like we used in our last lesson on exponential growth and decay. So we're trying to solve, in this case, for the exponent. On the exponential growth and decay problems, we were plugging in values for the exponent. Now we're going to be trying to find what exponents make these true. So we want to get the power term, the term with the exponent by itself. So in this case, we want to get this by itself, so we're going to add 7 to both sides. And now we want to use what we started at the beginning of this lesson. We want to convert from exponential form to log form. So remember, this will be log base, the same base, so base e, and we crisscross. So I've got of 12 equals 4a. Now we just talked about a few seconds ago when we did the calculator, log base e is the same as the natural log of 12. And we can calculate that. So let's bring the calculator over. So let's find the ln of 12. So we get, we'll just round it to 3 decimal places, 2.485 equals 4a, and now we just solve this equation, so we're going to divide by 4. And we get, to wrap this up, we get a equals 0.621. So if we put that back into our original equation, I'm not going to take the time to put that in the calculator, but if we put this into our original equation, it would make the equation true. So let's look at our last problem here. This is our power term or exponential term. We have a multiplication here, so I'm going to divide by 9. So I have 10 to the a plus 1 power equals 88 ninths. Whoops, what am I doing there? Now you could go ahead and convert that to decimal. I'm going to leave it as a fraction so that I'm not rounding. Now we're going to convert this to logarithm form. Oops. Of this number here, 88 ninths. And that's going to equal a plus 1. We crisscross. Now again, I picked one that is one of our common bases. So this is just log on the calculator. Now we can calculate this. So log of 88 ninths. And we get 0.9902. And we can subtract 1. So we're going to subtract 1 from that. And we get negative 0.0098 equals a. Now, if I had picked a problem where our base here was something other than e or 10, been 2 or 3 or 5 or whatever, then when we did this step here, we'll get to this step to calculate this, we would again be using that change of base formula on the last set of problems. So good luck. Logarithms sometimes seem mysterious, but the most important thing that we can remember are 2 things. We can remember that a logarithm is simply asking to what power or to what exponent do we raise this base to equal this number. And we also, most important, is converting back and forth to these bases. So the base of the exponent, it stays the base of the logarithm, and the 2 variables or the 2 terms on opposite sides of the equals trade places. They crisscross. Have a great day.
Are you ready? Are you ready?